I've got some free-form thoughts on continuous integration for software engineering, and I wanted to share and talk through some of them just to educate a bit people who might be less familiar with what it is or how it's used, how to get started with it. To start with, what is continuous integration? In software engineering, continuous integration refers to integrating the changes you make to your software as continuously as possible. And that's in contrast to waiting a long time before integrating any changes you've made, at which point you're not familiar. Maybe the thing that you changed 3 days ago broke what you were expecting as opposed to the changes 1 day ago. But how do you know the difference between the change you made a day ago and 3 days ago? Well, if you're continually integrating the changes you make over those 3 days, you'll know exactly when the change that you created broke things. So continuous integration is exactly what it sounds like. It's continuously integrating the changes you make to your software. Now, every time you integrate a change, you have to apply some kind of a check to verify that your change is not breaking the behavior you expect of your software or your software program. And there's a variety of these types of checks, but generally the most common type of check is to actually try running your software. And there's two steps generally to running software. One is that you first need to compile from the human readable programming language that you've written your software in to a more machine readable version of your code. And that mere process of converting from human readable to machine readable can often unearth problems and bugs with the change you've made to your software. So that's the first category of continuous integration check, is to try compiling the software. The second is you can write all kinds of isolated pieces of software that actually try to execute sub-portions or subroutines of your bigger program. The key here is that these pieces of software that are testing pieces of your main software are automatic. So every time you make a change, you can rerun these test programs, and these test programs will verify that the change you've made hasn't broken any existing functionality or existing expectations you've got about the behavior of your program. So those are the two most common types of continuous integration checks, the first being compilation and running, and the second being these types of partial tests that try and execute pieces of your bigger program to verify automatically that the behavior of your program hasn't broken. So I think it's helpful just for your own cultural enrichment to know where continuous integration as a concept originated from, and it wasn't software engineering, that's for sure. Software has only been around for less than half a century, and prior to that, there were a lot of areas of physical engineering that had a lot of need for coming up with ways to ensure that the engineering processes in manufacturing, being a big one, militarization, like airplanes and bombs and guns, civil engineering, like construction, physical construction of buildings and bridges, were reliable. And so continuous integration has been a tool of the engineering profession for a really long time. If you are curious how it got applied before software was created, imagine someone in the Civil War, American Civil War, who was trying to verify that every bullet that was being sent to the front lines and handed to soldiers could actually fit into the guns that all of these soldiers had been given. And how could you be sure that every gun given to the soldiers was capable of handling the same size ammunition, the same amount of gunpowder? So continuous integration has its roots in physical engineering, and you'll find that often coming up in software engineering is that many of the best practices we've learned in software engineering are stolen or acquired or learned from physical engineering. That leads us to the next question, which is deep on my mind, and I've thought about it in every software engineering job I've held, which is, what are some of the tricky issues and problems you'll encounter with continuous integration, because it sounds so great. It sounds like, you use it, make it a enshrined process in your business or your software project. Great, what could go wrong? And the reality is many things can go wrong, but the first and foremost is that there's a cost to process. There's no free lunch. When you use continuous integration implies placing checks and balances on what's otherwise a free process where there's no checks and balances. And the cost of that is that you'll encounter all kinds of maintenance costs for infrastructure relating to ensuring that your continuous integration is functioning properly. By that I mean, imagine there are false positives where perhaps your checks that you run every time you try to integrate a change of your software are actually incorrect, and you have maybe automatic tests that are indicating your change is wrong when in fact they're right. And if you didn't have that continuous integration check, then the change you do want to make to the software, and that is valid and you want it to be integrated into your software, would otherwise have made it in. So there's a cost to maintaining even just the automatic software checks that you've got. Maybe there's a new version of Java and there's a change in its compiler. And if you want to use the new compiler, you're going to have to retrofit your continuous integration process so that it uses the new compiler, just as everybody who's working on your software has to upgrade their laptops to a newer version of Java. These are real costs, and they're important to account for in engineering leadership decision-making or individual contributor decision-making. There's a trade-off to all processes that you impose on your business. So that's one of them. Another type of drawback you might encounter in adopting continuous integration and trying to write more automatic tests around your software is that you'll discover that there are some tests that exhibit inconsistent behavior. For example, someone might write a test that validates a subroutine of your program, and then they merge it into the shared main branch of your code, and it passed. That test, that check that passed, doesn't end up passing on your laptop. Or, God forbid, every 3 days it fails with an opaque error that doesn't reveal what the true cause is of the failed test. This is way, way more common than you might know. It's a really common category of problem for automatic tests. And it's a really common problem for software when it's running in production, whether on a server in the cloud or on a customer's device. And the key to this is to design tests and learn how to write tests that are hermetic. And the adjective hermetic is a rare English word, but it basically means that your code is running in an isolated state where it's not subjected to randomness. It's not subjected to randomness that might come from the environment outside of your software you want to test. This could be if your test uses a timestamp and it looks at the current timestamp when it evaluates the test. You can imagine if a test that ran that assumed that it's a weekday would lead to that test failing anytime it's ran on the weekend. So that's an example of a non-hermetic property of a test, and non-hermetic tests will cause you a lot of headache because you'll assume your checks are really valuable and they're helping prevent you from delivering software that's broken or software that creates bad experiences for your customers. But in fact, you can accumulate technical debt in your test code, not just in your customer code. So there are trade-offs to adopting continuous integration, is the only point I want to make. This leads to the last point I wanted to make in this video around how to get started. And what I would recommend in that regard is learning about how to write tests. Every programming language has tooling built into it that allow you as a software engineer to write tests. You'll commonly see this in Java, Python, Ruby, JavaScript with the keyword assert. And the way the assert keyword works in most programming languages is it's followed by a Boolean statement. So you can assert that some expression is true or false. And the value of these assert statements is that you can make assertions about what the state of your program needs to be at the point your assert statement is evaluated. And that's the basis for all tests, is you evaluate some piece of your software and you look at the return value and you make an assertion about what the return value looks like. Now there's a lot of variance and a lot of complexity beyond that, but as far as where you can get started today with continuous integration and writing tests, it's with using the assert statement and writing a maybe smaller program that evaluates pieces of your software while making assertions about what your expectations are to indicate that your software is working properly. Now that's a very abstract kind of bit of guidance I'm giving you. A little bit more concrete, I guess I could tell you, is that there are a lot of ways to set up computers besides the one where you're writing software so that when you want to make a change to your code as it's hosted off your development machine, you can get a server that runs your tests for you without needing to have your laptop on. And this is really valuable when you start working with more than just yourself on a piece of software. So if there's me and someone else collaborating and I make a change and push that change up to our shared code repository, maybe on GitHub, GitLab, Bitbucket, what have you, those hosting providers can trigger your tests to run on a dedicated server. And now there's a lot of different solutions to how you can perform that triggering of the continuous integration test suite, or the collection of tests that you want ran every time you are checking a change you want to integrate. But there's three main ones. One is to use the existing offering of your code repository hosting provider, whether that's GitHub, GitLab, Bitbucket, or what have you. At this point, there's a service offering called GitHub Actions. GitLab has its own continuous integration CI provider. Alternatively, you can use a third-party provider that's separate of your code hosting service. So you can have GitHub trigger a service like Travis CI is one of them. Circle CI is another. All of them have relatively generous free tier plans so that you can start using them without needing to pay them anything. Another option, which is what in my opinion, is the least desirable when you're first getting started out with continuous integration, is to administer your own server and install software on your own virtual machine, maybe on Amazon Web Services or Google Cloud or Azure, and run your software manually, administering your continuous integration code on that server yourself. And that comes back to my earlier point about the cost of maintaining continuous integration, is that it's really important to be aware of those costs and manage those costs. So that's kind of why I discourage you from getting started with continuous integration by setting up your own servers to run continuous integration. Better, in my opinion, is to start with some of these more managed services that have generous free pricing for when you're getting started up. So hope that's helpful. Curious to hear how your experience with continuous integration looks like. If you've got questions that I might have missed about what continuous integration is, or if I said something that's unclear, I'm happy to answer it in the comments. Feel free to subscribe. I'll be back with more videos later. Enjoy.